I want to thank the organizers of this meeting for the invitation to present to you today. Details on this research project called DDD-Africa, where we are exploring the utility of diagnostic exome sequencing in an African setting. I'm Zane Lombard, the PI of the project, but the work I will present today is entirely a collaborative team effort from the whole DDD-Africa team listed below. Developmental disorders represent a spectrum of lifelong disorders that are often presented from childhood and that impact an adaptive function on all three domains. This is conceptual, like language skills, social, as well as practical function. Developmental disorders include a spectrum of impairments, of which intellectual disability is the most common. It's thought that approximately half of developmental disorders are due to a genetic cause, and in severe cases, up to 80% of disorders could be genetic. However, genetic diagnosis is not straightforward, as this set of disorders are marked by both clinical and genetic heterogeneity. This Circos plot gives you a glimpse of this complexity uncovered by the DDD UK study, showcasing the variety of different clinical features oftentimes seen in developmental disorders and the variety of genetic loci found to be linked to these. We know that despite several decades of research and development, about half of children with a developmental disorder remain without a diagnosis. And unfortunately, the picture in Africa is much more dire. In South Africa, the majority of the country does not have access to genetic services, and we fall far short from the global recommendation for the number of medical genetic specialists and genetic counselors required to offer an appropriate service. Based on an internal patient file review that one of our students performed, focused on our genetics clinics, we see that the majority of patients who visit our clinics have a developmental disorder, and of those, 92% remain undiagnosed. So why is this important to get a diagnosis? Well, we've seen clear evidence that early and accurate diagnoses can be life-changing for patients with developmental disorders. Identifying a genetic etiology informs parents and other family members of potential future risks and improves clinical management. And even in situations where a diagnosis does not represent a cure, which is often the case, the end of the diagnostic odyssey has significant psychosocial impact for families. Families of children with undiagnosed genetic diseases often face an uncertain and unpredictable journey that can last for several years and with significant financial cost. This is a global issue, but even more pertinent in low resource settings. Here you can see a graph representing patients from our genetics clinic and the number of years as well as the money spent on this diagnostic odyssey. For many of our patients, the cost of cascade testing quickly moves beyond the cost of an exome sequence test, which could potentially yield results much faster. I realize that I don't have to convince delegates of this meeting of the revolutionary impact next generation sequencing and specifically exome sequencing has had on the field of genomic medicine. But given the scarcity of resources on the African continent, we're left with the question of whether exome sequencing is a practical first-line diagnostic strategy for developmental disorders in low and middle-income countries. This is then the main focus of the DDD-Africa project, where our rationale is to map the genetic etiology of developmental disorders in Africans, whilst catalyzing improved diagnostic services. This is a collaborative study across 2 African sites in Johannesburg, South Africa, as well as in Kinshasa in the Democratic Republic of Congo. And there's a strong partnership with the DDD UK group, and they have already demonstrated the value of adopting a comprehensive genome-wide strategy to elucidate the underlying causes of developmental disorders. DDD-Africa forms part of the H-Africa consortium, and alongside our goals of performing whole exome sequencing on 500 patient-parent trios, we are also focusing on training, capacity building, as well as community engagement. One of these activities that everyone has found extremely informative are our monthly clinical review and variant interpretation meetings. Originally, we planned to have these take place in person, but we've mostly had to move this to a virtual platform due to the COVID pandemic. This has had the positive effect that at least more students have had the opportunity to participate, and the discussions and learning opportunities have been plenty. So in the DDD-Africa project, we've established definitive inclusion criteria to ensure that we are enrolling patients from the more severe part of the spectrum of developmental disorders, as these patients are more likely to have a genetic cause for their disorders. These include patients with moderate to severe intellectual disability, as well as those with a specific major or minor organ anomaly. Patients excluded include those with a suspected multifactorial or environmental origin, and known conditions with no strong evidence for a monogenic cause. We're capturing all our clinical data on the Decipher database. This is an online tool which has ensured secure data sharing between sites and also implements fair data principles. Our patients represent the full spectrum of ethno-linguistic languages that are spoken across South Africa and the DRC. What you can see here in the inner part of the pie chart are the array of languages spoken by participants from the South African side, with 90% of participants being of African ancestry. For the DRC side, Lingala is the most common language and ethnic group represented. Our study also implements a tiered informed consenting process, giving participants control over decision-making regarding the reuse of data and samples, as well as the use of medical photographs captured as part of the clinical workup process. We believe that our approach is working well, and this is really reflected in the different decisions being taken, as shown here on the right. For instance, what you can see in the bottom pie chart is that the majority of patients are agreeing to broad sharing of data and samples, but are making much more reserved decisions and a much more variety of decisions when it comes to the use of photographs of their underage children. Regarding the sequencing and bioinformatics arm of the project, we've really been leveraging the strength of the DDD UK team whilst ensuring that we build appropriate capacity and expertise locally. We've had excellent support from the H3A BioNet's local network in setting up our bioinformatics pipelines. Thus far, we've sequenced 480 participants using the Wellcome Sanger Institute's Illumina NovaSeq platform. In addition, we've also done a small pilot project here in South Africa to establish the requirements for performing whole exome sequencing on our locally available INS5 instrument. So following a preliminary quality control step, all data that is generated in the UK are transferred to the WITS high performance cluster and are then further shared with the DRC team. We have set up an automated bioinformatics pipeline locally aligned to international standard practices, which is followed by then a manual clinical interpretation process. The pipeline has been implemented in Nextflow and documented on GitHub. Over the next few slides, I will present some of the preliminary findings from our first analysis of our whole exome sequencing data set. I just want you to note that I've also included some patient photographs in the coming slides where consent was given, of course, as the medical geneticists and dysmorphology experts in the audience may appreciate the opportunity to compare and contrast key phenotypic features with some of their own patients. So overall, we obtained excellent quality data with a median depth of 55x. The number of mean and novel variants that we observe in our exome sequencing data set are actually significantly higher compared to exomes from the European patients shown on the left here. And this can be expected given our knowledge of the genomic diversity of African individuals and due to the fact that we are using the standard Build 38 genome reference and not a more sophisticated pan-genome or genome graph at this stage. The downstream implications of this is that our filtering process will result in many more variants to consider than is the case with other patients. As you can see here on the right, at the bottom of the pyramid, we're left with a manageable number of variants previously implicated in developmental disorders for the majority of the exomes. These are our so-called low-hanging fruits, and that would be investigated first. However, if none of these variants turn out to be likely disease-causing, we have a much more involved investigative task to complete. The following results that I'm going to present will focus on the analysis that we've performed using our small nucleotide variant and indel pipeline. We plan to also evaluate de novo mutations, copy number variants, as well as cases of suspected mosaicism and UPD. And several of our trainees involved in DDD-Africa are working on implementing these additional analyses pipelines in the meantime. So from our in-house whole exome sequencing study, we were able to identify putative disease-causing mutations in 6 of the 7 patients, and we were able to validate these variants in 5 of the patients. This investigation identified a patient with Takanushi-Kozaki syndrome, which to our knowledge is the first reported case in Africa. This is patient 1. We also identified 2 cases of mandibulofacial dysostosis with microcephaly in patients 3 and 7, followed by congenital muscular dystrophy and mental retardation type B2 in patients 4 and 5 who are fraternal twins carrying the same compound heterozygote mutation. Patient 1 was initially referred to the genetics clinic at the Rahima Musa Mother and Child Hospital in Johannesburg, South Africa, at the age of 6 months for assessment, and this was on the basis of her cardiac disease and associated dysmorphic features. A cytoscan HD array was performed and reported as negative, and several other investigations did not yield any feasible answers. She was enrolled in DDD-Africa at 10 years of age. The identified de novo mutation in the CDC42 gene identified using exome sequencing was classified as likely pathogenic based on its absence in population databases, the fact that there were 2 pathogenic submissions in ClinVar, as well as in silico functional study evidence showing the variant to have deleterious effect. Based on the diagnosis made, we were able to make further recommendations for care and in this long diagnostic odyssey for this particular patient. The second case I want to share with you demonstrates the scope of African genomic studies to improve clinical dysmorphology. This is a 9-year-old female patient of North African descent with moderate intellectual disability, ventricular septal defect, hypertonia, dysmorphic features, macrocephaly, as well as short stature. Our clinical team posited a diagnosis of Cornelia de Lange syndrome based on these phenotypic features, but our exome analysis actually revealed an ARID1B frameshift deletion, with evidence suggesting it to be likely pathogenic. So we know that mutations in ARID1B are known to cause Coffin-Siris syndrome, which is a rare clinical heterogeneous disorder. Our clinical team noted that this patient actually presents with very specific features that may present a distinct African gestalt, which could be utilized to update and refine dysmorphology analysis. The suggestion was to follow up with additional phenotyping before we confirm this diagnosis. We also noted that with Coffin-Siris syndrome and other related syndromes, that they present with distinctive DNA methylation episignatures that have demonstrated diagnostic utility. And we are currently looking into opportunities to confirm if this is also applicable to our patients, and this information can then be used in future to resolve ambiguous clinical cases or to reclassify those with variants of unknown significance, and even to identify previously undiagnosed subjects through targeted population screening. The final case shows the utility of exome sequencing also to confirm clinical diagnoses. This 6-year-old patient was born with a limb defect and syndactyly, and both mother and child have intellectual disability, with mom also presenting with a tongue abnormality and cleft lip, brachydactyly, as well as renal cysts. Our clinical team suggested that the clinical presentation aligned with oral facial digital syndrome type 1, and this diagnosis was actually confirmed by the exome sequencing, and of course that presented a service that we were not able to offer previously to these patients. We're hoping to confirm a diagnosis in the mother in future, as we know that adults with idiopathic intellectual disability oftentimes have not had genetic testing done, as is also the case here. So I hope that today that I've demonstrated to you that our preliminary findings underscore the potential of an exome sequencing diagnostic approach for rare developmental disorders in a resource-constrained environment. We're gathering evidence that show that whole exome sequencing will be cost-effective and beneficial to patient care in the long term. And although this test is currently still costed higher than traditional testing options, the question really is not how much will it cost, but rather how much will we save in the long term, both for the patient and the family, and also in the local public healthcare system. Over and above this, proving feasibility of local implementation would allow us to step into the future and towards genomic medicine services in Africa, and also lead to job creation and local skills development. I would really like to thank the NIH and as well as some of our local funding bodies for providing funding for this study. I'm also very thankful to our many excellent collaborators, both in the AfSHG Consortium and beyond. And a special thank you also to the DDD-Africa research and administrative team. Just want to end off by saying that if you're interested in learning more about the DDD-Africa study, or even to possibly become a partner site, please feel free to email me, or you can reach out to me on any of the social media channels provided in my bio on the online conferencing system. Thank you so much for your attention, and I'm happy to answer any questions that you have.